Okay, we're now going to be looking at the field of a polarized object. But in order to get there, we're going to need to pull together a lot of the things that we've already seen. And one of these things we haven't formally derived yet, because we're going through what was in chapter 1 when it becomes relevant. So what we'll do is we're going to derive that neat little expression now, and then we will use it to come up with a nice way to write down equations for polarization. Okay, so the expression that we want to show is that the gradient primed, we'll talk about exactly what that means in just a minute, of 1 over curly r is equal to curly r hat over curly r squared. Okay, so remember curly r goes from, it's a displacement vector from x prime, y prime, z prime to x, y, z. So how we can write it down as a vector is that curly r is equal to x minus x prime, and that's in the x direction, plus y minus y prime, and that's in the y direction, plus z minus z prime, and that's in the z direction. So this is the vector. If we want the magnitude of it, then curly r is equal to x minus x prime squared plus y minus y prime squared plus z minus z prime squared, and we're going to take the square root of that thing. Now we're going to be doing differentials, derivatives with this, and it's kind of easier to use the chain rule in parts of it. So let's let u equal x minus x prime squared plus y minus y prime squared plus z minus z prime squared. So you can see that this, if we're relating this back to this is equal to the square root of u. But we'll do this so that we can show that du dx prime, just because this is going to be useful later. If we take the derivative of all of this with respect to x prime, then these terms are all constant, and so they disappear when we take the derivative. And what we're left with is 2 and then x minus x prime, and then we need to times it by minus 1. So this is going to be equal to minus 2x minus x prime. Okay, so what we're trying to do is work out this. So what this means is d dx prime. So we've got the prime on the x here because we've got the prime on the grad here. That's what that means. And so then we've got 1 on r, and we've got r here. So this is going to be x minus x prime squared plus y minus y prime squared plus z minus z prime squared, and this is to the minus a half, plus we'll have d dy prime of the same thing. This is going to take a while to write out. Plus d dz prime and I've left off my vectors. This should be times x. This is in the x direction, this is in the y direction, and this is in the z direction, because when we take the gradient of a scalar, we get a vector. Okay, so now what we're going to need to do is we're going to need to differentiate this, but this is part of why we use this u over here. This is u to the minus a half, and we know that d dx prime of u to the minus a half is equal to du to the minus a half du du dx prime, which is why we did this over here. So in this case, when we're differentiating u to the minus 1/2 with respect to u, that's going to be equal to minus 1/2 u to the minus 3/2. And then we need to times it by du dx prime, which is times minus 2 times x minus x prime. And so when we multiply these, we're going to end up with plus 1. And so this is going to be equal to x minus x prime times u to the minus 3 on 2, where u is this thing up here. And we'll end up with a similar thing for each of the directions. It's just in the y direction, this will be y minus y prime. And in the z direction, this will be z minus z prime. Okay, so we can write this as equal to x minus x prime, and that'll be times x. And this is over u to the minus 3 on 2, which is x minus x prime squared plus y minus y prime squared plus z minus z prime squared. And this is to the 3 on 2. And this will be plus y minus y prime y plus z minus z prime z. Okay, so on the top, we have got this vector here. So we've got our curly r vector. And then on the bottom, we've got this, except that it's to the power of 3. So we've got curly r cubed. So we can write this as r hat divided by r squared. And so that's a substitution that we're going to need to make in our derivation. So now we're going to consider the electric fields and potentials and things caused by these bound charges moving to give a polarization. So we're going to be trying to answer problems where we're given the polarization. So if we suppose that the polarization is given, and what we want to work out how to do is to find the field produced by the object. So for now, we're not worrying about the field which is causing that polarization in the first place. We're saying, given that we have this polarization, what field is this polarized object going to produce? And the approach we're going to use is the normal one. We're going to break our continuous object up into lots of little parts, and we'll end up summing these parts together to get the total answer. And we'll start by calculating the potential because this is a scalar and so easier to deal with than the electric field. Okay. So let's start just by considering a single dipole. So we have done that before. This derivation is going to bring together a lot of different things that we've seen. So I'll be noting where we've seen them so that hopefully this will make a bit more sense to you. So you've seen previously how to calculate the potential for a dipole. So the potential for a dipole V of R is equal to 1 over 4 pi epsilon naught, 1 over curly R squared times curly R hat dot P. Okay, but this is just for a single dipole. And we're considering a continuous object. So let's draw our object here. Here's our object, some random shape made up of some volume. And let's consider a little volume increment in here. And this volume increment has volume d tau prime. So this is the volume. And what we're asking about is, well, what is the potential at this point R over here? So this little volume here is at a location r prime. So we're taking the prime location as inside our object, and our curly r vector is going from this volume increment to where we're measuring the potential. So this is our curly r vector. And the dipole, the little p of this volume increment here, is equal to the polarization times the volume, because the polarization is the dipole moment per unit volume. So what we can do now is replace this dipole moment with this polarization. This is a vector, polarization is a vector, and this dipole moment is a vector. So we're going to replace this dipole moment with this, and we're going to get the total voltage, we're going to have to integrate all over this volume. So when we do that, we can write this equation out as 1 over 4 pi epsilon naught. Now we're doing the integral over the volume, and we've got curly r hat dotted with p, which we're replacing with the polarization d tau prime, and then we're dividing this by the curly r squared, because we've got our curly r squared here. So now what we want to do is do this integration, but it's a bit messy at the moment, which is where this relationship over here comes in. So let's just really clearly mark out where we've used everything. So this thing we use to write down this, and what we're going to do is take this thing now, and we are going to replace this part with this expression here. So this will go in here. And when we do that, we can write this out as 1 over 4 pi epsilon naught, and we're integrating over volume. And now we've got, let's switch the order between these two terms, because it's just a dot product, so we can switch the order. So we can write p dot, and now we've got grad of 1 over curly r d tau. Okay, and now you'll just have to trust me why we do the next step. What we're going to use now is this product rule number 5 from the front of Griffiths, which is going to let us write a vector dotted with a gradient. So here we've got our vector dotted with a gradient, and that is equal to the gradient of the function times the vector. And then if we move this over to this side, minus the function times the divergence of that vector. So we're going to use this to rewrite this expression now, and you will see why in a little bit. So now we're going to use this with this to get our next line. So now we've got 1 over 4 pi epsilon naught, and we're splitting it into two terms. So we've now got two integrals, and the first one is the integral over volume, and we'll do this first term here. So this is going to be the gradient of 1 over curly r times p d tau. And then we've got the next term, which we need to subtract off. So this will be minus the integral over the volume of 1 over curly r times the divergence of p. And now finally what we can do is use the divergence theorem, which is written over here. So we are going to use this equation here to replace this this part here. We've got a volume integral, so we're going to replace that with the integral over the surface. So this is equal to 1 over 4 pi epsilon naught times my surface integral, and this is over a closed surface of our field, which in this case is the polarization divided by curly r, dotted with n ds, and then we'll keep this other part of the integral as it is. So this is 1 over curly r times the divergence of P d tau. So now we've come up with an expression for the potential, and on the next slide where we've got a little bit more space, I'll show you why we would want to do it this way. Righto, so this is the equation that we just derived for the potential at position R due to this volume with a polarization given by capital P. And now we're going to see why this is a useful form. So what I want you to do is to compare this part of this integral with the expression that we were using over in this previous lecture for the potential when we knew the surface charge density. So you'll see that the form of these two are remarkably similar. We've got the 1 over 4 pi epsilon naught on both of them. On this one, we've got sigma divided by curly r. Here we've got this P dot n, and we're dividing by the curly r. And then this is times the surface area increment dA. And ds dash there means the same thing, that surface area increment. So this formula here and this formula here are the same if we replaced the surface charge density here with P dot n. So let's just make a note of that. We've got that our surface charge density, which we're going to call sigma b because it's due to the bound charges, is equal to P dot n, where n is the normal vector there. And we'll put this in a box because this is an equation that's going to come up a lot. So the surface charge density for these bound charges is given by the polarization vector, the dot product of that with the normal to the surface. And this is a closed surface here. And then it should all just work the same as it did for a normal surface charge density. And considering the second part of the equation here, where we've got the volume integral and we're taking the divergence of the polarization, this has a very similar format to the equation down here, which was our equation for the potential of a continuous charge distribution with a charge density rho. So you can see we've got the 1 over 4 pi epsilon naught in both of them, the 1 over curly r in both of them. Here we've got the volume charge density, whereas here we've got the divergence of the polarization, and then we've got multiplied by the volume increment. These are both the volume increments, so they're the same things. So in this case, if we let the volume charge density be equal to, we've got a negative here, which we didn't there, so we better have this negative times the divergence of P, then this is going to work out in the same way as well. So we can actually write down that sigma b is equal to minus the divergence of the polarization. Now, we don't have to worry about this little prime here. This is showing that this is at this point inside the volume. Here, we'll take the divergence inside the volume, so we don't need to mark that down. So let's put a box around this one as well, because that equation is also going to be important. So I think the easiest way to see why we would want to do this is by having a bit of a look at an example. So let's have a look at an example problem now. Righto, so in this problem, we've got a sphere of radius r that has a polarization which is equal to kr. So this is a radial polarization in this case, and we're talking about a sphere. So it sounds like spherical coordinates are going to be the best way to deal with this problem. And we're told k is a constant and r is the vector from the center. Part A asks us to calculate the bound charges, sigma b, which is the surface charge density, and rho b, which is the volume charge density. And part B says to find the field inside and outside the sphere. So we're going to be making use of the equations that we have just come up with. So the surface charge density is given by the polarization dotted with the normal vector, and the volume charge density for the bound charges is given by minus the divergence of the polarization. Okay, so let's write it out in full. Part A, we will do spherical coordinates, and I'll write out the full vectors. I mean, you can probably see that the theta and the phi components are going to be 0, so you don't necessarily have to write everything out, but I just will so that to make it clear. So this is my p vector, and I'm taking the dot product of this with my normal vector, which is 1, 1, and r sine theta, but r is 1, so that will be sine theta. And so you can see that the only component that we're going to get is kr. And the bound charges are all bound on the surface at radius r. So at surface, little r is equal to big R. So this means that the charges bound on the surface are going to be given by K big R. Okay, now we also have to calculate the volume charge density. So in order to do that, we will need to use that the volume charge density is equal to minus, and now we're using spherical coordinates, and we're going to take the divergence. So this would be 1 over r squared d r squared, and then if we had theta and phi components, which we don't, but just in case you ever get one, let's write this out. And then 1 over r sine theta d phi, and we take the dot product of that with kr 0, 0. And so you can see we're only really going to have to worry about this term here. So that term is given by minus 1 over r squared dr of r squared times kr. So this is equal to minus 1 over r squared of dr of kr cubed. When we take the derivative of kr cubed with respect to r, we end up with 3kr squared. These will cancel, and we end up with minus 3k as the answer for that one. So we've answered part A. Let's do part B in a slightly different color, just so that we don't get confused about where stuff is. So part B says find the field inside and outside the sphere. Okay, so now we've got the surface charge density on the sphere and the volume charge density inside the sphere. So now this means that we can just go back and use the techniques that we're really familiar with in order to calculate this. So we can actually use Gauss's law for this. So if we draw our sphere here with radius r, and we know that at its surface it's got that charge density sigma b, and inside it's got the charge density rho b. And then when we're considering inside, let's do inside in green. We're going to take a Gaussian surface like this with radius r, so r is less than r, and Gauss's law tells us that the integral of the electric field over that surface is equal to the enclosed charge divided by epsilon naught. And then this is all symmetric, so we can assume that the electric field is going to be constant over this surface here, and this integral of dA is just going to be the surface area of this sphere here. So we can say, well, this left-hand side is going to be equal to E times 4 pi r squared. And then the right-hand side, we've got the charge enclosed there. So that is going to be the charge density times the volume, which will be 4/3 pi r cubed divided by epsilon naught. And so you can see a lot of these terms are actually going to cancel out. The 4's will cancel, the pi's will cancel, that r squared will cancel with that one. And we have an expression for rho b. We've got that here, rho b is equal to minus 3k. So we can write this out as E is equal to minus 3k. And then we've still got the 1/3 r on top divided by epsilon naught, so those 3's will cancel, and this is equal to minus kr divided by epsilon naught. So now we've worked out the electric field inside there. Electric field is a vector. So this here, we were making the assumption that E and dA were in the same direction. So that's radial. And this R can also be a vector. So we can put that, and then that's showing that those are both radial vectors. Okay, so let's change colors again and do outside. So outside, where r is greater than r, in that case, we're going to take a Gaussian surface like this. And then we have the same equation, this equation for Gauss's law. And we're going to have to calculate the enclosed charge. So here we didn't need to consider the surface charges because they were outside our surface. When we're doing this volume, we need to consider the surface charges and the charges inside that purple sphere there. So we can do that the enclosed charge is equal to the surface charges times the surface area, which will be 4 pi r squared, plus the volume charges times the volume of the sphere. It's only inside the purple sphere that counts. So this is 4/3 pi r cubed. There are no charges in this region here. Okay, so this is equal to sigma b, which we calculated up here. So we will substitute that in. That is kr times 4 pi r squared plus rho b, which is minus 3k times 4/3 pi r cubed. Those 3's will cancel. And now you can see that these two terms are going to perfectly cancel each other out. So this is going to be equal to 0. And so when we're considering this equation here, we're going to have that this thing is equal to 0. And since the surface area is not 0 and E and dA are we'd expect them to be parallel, then that tells us that the electric field must be 0. So E must be 0. So you can see how using these equations here has made it possible to fairly easily deal with questions about polarization using things such as Gauss's law that we're already very familiar with. Now, you may be feeling a little bit uncomfortable with how we derived these expressions for the surface charge density, the polarization dotted with the normal vector, and the volume charge density, the negative divergence of the polarization for these bound charges, and thinking that, well, that was all just kind of mathematical trickery. And is this actually something which is physical? Do we really have these charges on the surface? Do we really have this charge inside? And the answer to that is yes. So what I'm going to try and do now is come up with a bit more of a physically intuitive, though slightly less rigorous way of showing these equations, or at least showing that these equations physically make quite a lot of sense. Okay, so to start with, to kind of show you that we do get a real distribution of charges, I want you to imagine placing lots of dipoles in a line. So we're going to line up lots of dipoles end on end like this. And let's think about the charge distribution caused by this. So remember, a dipole points from a negative charge. So each of the ends of these arrows has a negative charge, and it points towards a positive charge. So we've got a positive charge at each of these ends of the arrows like this. Now, hopefully from this diagram, you can quite easily see that in all these middle bits, we've got a positive and a negative charge cancelling out. So all along here, when we've got this constant dipole moment, which would, because the polarization is the dipole moment per unit volume, this is going to give us a constant polarization. All along the middle, the charges are cancelling out, and so it's neutral all along here. But at these ends, we've got charges left over. So we've got a negative charge at this end and a positive charge at that end. Okay, so remember this is for bound charges. So these electrons, all the electrons within the material are still stuck to their atoms, but they have polarized themselves a little bit and separated a little bit. Well, the nucleus and the electron cloud have gone to slightly different ends. And so because that's happened to all the material in between, we've effectively ended up with a large separation of this positive and this negative charge. So one way we can use this to solve charges, where we've got kind of like this constant polarization, is that we can imagine that our object is constructed of negative charges. So these are negative charges with a charge density of sigma negative, and then we've got positive charges with the same charge density, which is shifted just a little bit this way. So this is positive and this bit's negative, and this is our positive charge density. And yet everywhere in between here, the charges cancel out. So we've got no charge there, but we're then left with this negative end down here and a positive end up here. So this can be a useful way to set up problems. Okay, but to show that this equation here makes sense, let's consider a cylinder like this with a constant uniform polarization like that. Now, because we've got a polarization like that, we know that we've got a negative end down here and we've got a positive end up here. Now, let's start by considering a tiny chunk here. So we're going to take this little chunk here. So let's take this down here, and this little chunk here. We'll let it have length D, so that is length D. It's got an area A. This will be our negative end. This will be our positive end. And because P is our dipole moment per unit volume, we know that the dipole moment, P, is going to be equal to the polarization times the volume. And so this will be times AD. So that's one way that we can write down the polarization. And we also know that a dipole moment from when we first derived it is equal to QD. So we've got the positive charge here and the negative charge here, and they're separated by a distance d here. So this is equal to QD. So this tells us that the charge is equal to PA. And so if we want to get the surface charge density, that's going to be equal to Q over A, which is equal to PA over A, which is equal to P, which is consistent with this equation for this case because our normal is parallel to the polarization vector, and so that's what it would give in this case. So we've shown, at least for this case, that it's consistent with that through physical reasoning. But let's now imagine that we take a not quite so neat cut. Let's take an oblique cut this way. So in this case, we've got a piece which looks more like this. And this is the angle theta here, and this is our normal to the surface, but P is going this way, and we've got an angle theta in there. Now, in this case, we've still got the same charges over these total surfaces because we've always got a negative charge the way we've drawn it on the left end, and the positive charge, the same positive charge on the right end. But what's different now is this surface area here. So this surface area, let's let it be a end. And hopefully you can see from the geometry for this, this down here, if we took a cut here, this would have surface area A, but we've moved it up to this angle theta here. So considering this triangle here, this is A, and this is kind of A end. And so A end is equal to A cos theta. So this tells us that A end is going to be equal to A divided by cos theta. And so in this case, sigma B is going to be equal to, again, it's just Q over A, but in this case, the A is the A end. And Q we've said is the same, so it's still PA. And then A end is A over cos theta. So this is equal to P cos theta, which is the dot product between P and the normal vector. The angle between these two is cos theta. So hopefully that's kind of satisfied you that physically this makes sense. Now, in order to consider this volume 1, I want you to start by considering a sphere here. And let's just start with no polarization. So there's no net charge within our sphere. But now what we're going to do is we're going to add some polarization. And because we don't want everything to be zero. So we want some divergence, and hopefully you realize that divergence means that there's, like, we've got a sink or a source. There's arrows going out of a surface. So in order to have some divergence in this case, let's draw our dipole moments like this. So we're introducing new dipole moments. Okay, so we've done something, and suddenly we've applied an electric field or something that has polarized these molecules. So now we have negative charges inside the surface, and to make these dipoles, we had to move positive charges outside of that surface. Okay, so let's write down what we've done. So we're going to write down an expression for the charge inside the surface. So to get the charge inside the surface, that's the volume integral of the volume charge density over that volume. And in order to do that, we said that we had to move our surface charge density for these positive charges outside. And so this is sigma B dA, and we needed to move them out, so negative, because they're going to go out of the surface. And so when we move those surface charges out, that is equal to P dot N dA. And now what we can use is the divergence theorem, which lets us go back from a surface integral to a volume integral. So this is equal to minus the volume integral of the divergence of P d tau. And now what you can see is that this is equivalent to this thing here. But this is a vector. I should have marked that as a vector. So hopefully that satisfies you a little bit, that this one holds as well, that the charge density inside the surface is given by minus the divergence of the polarization. So in this problem, we have a very long cylinder of radius A. So let's sketch it out. Here is our very long cylinder. Sorry that my straight lines aren't especially straight. And it's got radius A like that. It carries a uniform polarization P perpendicular to its axis. Okay, so let's carry on drawing the axis all the way through here. And we're going to let the polarization P be pointing up like that. And remember that polarization points from the negative to the positive charge like that. And we're asked in this case to find the electric field inside the cylinder. Okay, so a useful way to model these types of questions is to imagine that the polarization causes the positive charges to move up a small distance. So we've got this positive cylinder of charge here. And here's the center of this cylinder, and it has moved up a distance d on 2, and it's got a charge density rho plus, and the negative charges have moved down a distance d on 2. So here's the center of this one. This is distance d on 2, and these charges have moved down like this. And this has got a charge, minus rho. These are equal and opposite charges, so I should probably write this as positive rho instead of rho plus. So this is positive rho. So you can see that effectively inside where the green and the red overlap, that's neutral like we discussed, but we've got extra positive charge up here and extra negative charge down here. Okay, now if we want to find the electric field inside the cylinder, let's work out how we could find the electric field a distance s above the axis of the cylinder. So let's consider this point here, which is a distance s above the cylinder. I haven't purposely drawn it on that green line. That's just a coincidence. This S is anywhere. We've got S is less than A. Okay, so how we always approach these problems when we want to find electric fields is with Gauss's law. And we're now going to need to consider our two charge distributions, our positive and our negative charge distribution. So let's start with positive. So this is the axis here for the red one. And so this distance here is S minus d on 2. So we're going to want to make sure that our Gaussian surface that we choose in this case is symmetric for the positive charge distribution. So we're going to take a little Gaussian surface like this. Let's let it have length L, and the radius for this one, radius, is going to be equal to S minus D on 2. And so Gauss's law tells us that the electric field dotted with the area is equal to the enclosed charge over epsilon naught. And so we can assume that the electric field's uniform over this surface. We'll ignore these surfaces because it's perpendicular there, so the dot product's 0. And so we can say, well, this is going to be E positive dA, and the area of this is L times 2 pi r, which is S minus D on 2, is equal to the enclosed charge, which is going to be the charge density, rho, times the volume, which is 4/3 pi, it's not a sphere, it's a cylinder, so this will be times L times pi r squared, which is S minus D over 2 squared, divided by epsilon naught. So one of these will cancel with that. These pi's will cancel, the L's will cancel, and we end up with E plus is equal to S minus D over 2 rho divided by 2 epsilon naught. Okay, so we've got an expression for the electric field due to the positive charge there, and now we're going to need to do one for the negative charge. So in the case of the negative charge, here's the axis for the negative charge, and there's our point S. So we will be drawing a sphere like this. Not a sphere, sorry, a cylinder. Keep on saying sphere instead of cylinder. So in this case, the radius for our cylinder is equal to S plus D on 2. And we've got that we're going to substitute into Gauss's law again. But in this case, we've got E minus times L times 2 pi S plus D on 2 is equal to minus rho, in this case, times L times pi times S plus D on 2 squared divided by epsilon naught. We can do similar cancellations. Let's make sure that we get everything, that and that. And so we end up with E minus is equal to minus rho S plus D on 2 over 2 epsilon naught. And now we know that electric fields obey the law of superposition. So we know that the electric field is equal to E plus plus E minus. And so that is going to be equal to rho over 2 epsilon naught. And then we've got S minus D over 2 minus S minus D over 2. So these S's will cancel, and we end up with, minus D on 2, minus D on 2. So that is minus D. So this will be minus rho D over 2 epsilon naught. Okay, now the problem is that in the question we were given the polarization, and this is not in terms of the polarization. This one is in terms of rho. So what we're going to want to do is replace rho with an expression for the polarization. So we know that the polarization is the dipole moment per unit volume. So we've got that the dipole moment is equal to the polarization times the volume. And in this case, our total volume is the length times pi a squared, and the dipole moment is also equal to the separation of the charges. So how much these two are separated. They're separated by this distance d here, so it's the distance times the total charge. So the total charge is just going to be that charge density times L times pi a squared. That's the volume, times D to get our dipole. And so we have done this to show that these bits cancel, and so this lets us write that rho D is equal to the polarization. So we can now substitute this in here. So this is equal to minus P over 2 epsilon naught. So we've now come up with a way to get the electric field for this situation.